Can we run a mid-tier coding agent on a budget GPU without waiting forever? Yes, definitely. The challenge is agent design. They process lots of documents, content, files, and huge system prompt instruction sets, often multiple times. In this video, you'll learn the 5 things needed to run a powerful local LLM without breaking the bank. We hit 1,142 tokens per second prompt processing and 40 tokens per second decode at a mid-frontier level. Run it from anywhere, even a coffee shop, swap between models, and find the best settings for your machine to get the most from your rig without pulling out your hair. We've seen how to offload models efficiently for good token generation speed. But no matter how much we optimize, offloading will never beat a model fully loaded into GPU VRAM. Since this budget build uses offloading, the key choice is how much stays in system RAM versus how much we pull back to the GPU. The part running through system RAM and CPU is limited by PCI bandwidth, RAM speed, and CPU cores. With DDR4 RAM, you bottleneck around 54 GB per second, becoming your token generation limit. Your system can pull Mo experts from RAM at about 50 GB per second. So if a model needs to pull 1 GB of experts per token, the maximum is around 50 tokens per second. 2 ways to improve. Offload less to system RAM so fewer experts pass through the CPU, increasing token generation speed. Second, CPU cores matter for parallel processing. The hardware priority is first VRAM, then RAM speed or PCI speed, then CPU cores. For this budget build, we're using the RTX 3060 with adequate VRAM for the price. DDR4 RAM is fine. I'm reusing an old CPU with only 4 cores. If you already own a GPU with less VRAM, these same techniques apply to get more out of your GPU. For the model, we're choosing an Mo. Some say Mo models aren't as good, but they're much more efficient for their size. A 30 billion parameter Mo model can run at the speed of a 3 billion parameter model. A dense model uses all its neurons to predict every token, while an Mo selects only the knowledge it needs, which is far more efficient. Yes, sometimes it selects the wrong knowledge, but frontier models use Mo architectures for the same reason. Now we can get even more out of the Mo model using REAP. A Cerebr's paper shows how to trim underperforming experts. On human eval, the prune 23B variant scored 95.1 versus 94.5 for the unpruned base. REAP removes 20 of unused weights, so more layers fit on the GPU. The 2 REAP models we're using are Qwen 3.6 Mo from Unsloth and GLM 4.7 Flash REAP 23B with a 20 ratio, reducing size to 80 of original. I use Q4 quantization, specifically Q4 KM or Unsloth dynamic quants. Anything below Q4 starts to break, but at Q4 you hardly lose any performance while getting a model 4 times smaller. These are mid-frontier level models. The sweet spot is 20 to 40 billion parameters, 1 excellent for coding, 1 faster generalist. We'll mix and match them with llama.cpp. Now the optimization phase. We need prompt processing speed, not just token generation. Agents are mostly prefill, long system prompts, MCP content, tool details, documents, and code files. First, cache reuse. On the first agent run, llama.cpp caches the prompt automatically. But if something changes in the context, the entire cache invalidates and reprocesses from the start. Cache reuse fixes this by splitting the prompt cache into 256 token chunks. When one chunk changes, only that chunk is reprocessed, improving time to first token. Next, tune 2 parameters, threads and ubatch. On a 4-core CPU, threads can go from 1 to 4. Ubatch can go from 16 to 32K tokens. Use llama.bench to find the best values. On Qwen, thread 1 gives 28 tokens per second, thread 3 peaks at 39.5, and thread 4 collapses to 22. On GLM, 45.77 at thread 3, 27 at thread 4. Leave the CPU 1 core for scheduling. For ubatch, our scenario is bandwidth bound, not GPU bound. Higher ubatch makes prefill faster. On Qwen, ubatch 256 gives 300 prompt processing tokens per second. At 2048, it jumps to 1142, almost 4 times faster. GLM goes from 446 to 863. TG stays flat. In production I use 1024. 870 tokens per second, leaving VRAM for offloaded layers. For KV compression with Turbo Quant, use Turbo 4 for keys, near lossless, and Turbo 2 for values. On GLM, Turbo KV gives plus 12 decode but costs 25 prefill. On Quen, plus 4 prefill and plus 5 decode a straight win. The bigger the model relative to VRAM, the more KV compression helps because freed VRAM lets us pull an expert layer back to GPU. For this setup, we're choosing Pi Coding Agent because it's lightweight, highly customizable, and has native llama.cpp support. No third-party middleware or proxy bridge is needed. We connect directly to Llama server by installing one package, pi install npm llama.cpp. This extension automatically discovers the models on the Llama server, their presets, and modality. After installing, update settings.json with the Llama server URL. Agent frameworks depend heavily on prompt processing speed because they read the full system prompt, make tool calls, read files, and edit content. The first agent run is slower because it processes the system prompt from scratch. Later turns are faster due to cache reuse. You only pay for the delta. Tool calls for reading, writing, and editing run smoothly. You can see the reasoning panel so the model's thinking isn't a black box. Everything runs at around 1000 tokens per second. Next, we'll configure Llama server to switch models directly from Pi without stopping the server. And as a bonus, we'll access the model from anywhere. Right now, Llama server runs only one model at a time. Switching models requires killing the server, changing the path, and adjusting tuning. Llama.cpp solves this with model presets. Create a models.ini file with settings for each model, then start Llama server with the preset file. Pi discovers available models through the model's endpoint. The server stays running. In Pi, type models to see the list, select one, and Llama server unloads the current model and loads the new one. Now for remote access, install Tailscale on your AI rig and laptop. Use the Tailscale IP as your Llama server URL. This lets you access the server from anywhere, giving you the same coding experience as a cloud agent like Claude Code. With that, you have a mid-frontier AI agent on consumer hardware, a roughly 280 GPU, quantized REAP models, a tuned Llama server, Pi Coding Agent, and Tailscale. No subscription, no API key, no rate limit. It's yours, and you can run it as much as you want for just the electricity cost. That's it for this video. Use these settings to tune llama.cpp or your local agents for your hardware. People often optimize for token speed, but for agents, prompt processing speed matters more. Keep experimenting, optimizing, and running LLMs locally. See you next time.